minutes late. So, so I'm Nimit, and this is a talk about the fellowship. How many people here are interested in hearing about the fellowship? Okay, all right. So almost nobody, and so that's good. So, ooh. So this is a sentence, in a sentence, what the fellowship is about. You have come to Full Stack with Grace Hopper for a, I guess if you count foundations, like a 4-month period of focusing on something and learning something. And in a sense, the fellowship is an extension of that, where you spend another similar period, but now you're focusing on the teaching side of things, on working with students, on diving deeper into the things that we're learning here. And so I'm going to talk more about the specifics of what the fellowship is, what your role would be, what kind of work you would be doing, the logistics of it. And if you have any questions, feel free to raise your hand at any time. There's no help tickets in this. All right, so anyone remember this pyramid? You saw it a few months ago. And the reason I bring this up again is because just to point you to where a lot of the fellowship is, which is in this area here. The important thing is that, and actually that's something that's a highlight of the fellowship itself, which is that it is a period, like you're going to spend your whole life as a developer, right? You're going to spend a lot of your life as a developer, and at least having the skills, and maybe not always being a software developer, but using those skills. But this is a concentrated 3-month time where you get to be a teacher, a mentor, somebody who is on the other side of the table, and that's really the core of what the fellowship is about. So, what will you be doing during the fellowship? Well. One of the most primary things you'll be doing is working with students. How many people here know a fellow? Okay, so since you know a fellow, you know that fellows help with academics. Another very important part of what fellows help with is admissions. How many people here were interviewed by a fellow? Okay, also a lot of you. And the admissions part of it is very important because one of the key things that a student who is applying to Grace Hopper or Full Stack is thinking or is wondering is, what is this experience like? And the reason that we really like having fellows on the interview side is because who better to ask that to than to somebody who's just kind of gone through that experience, who can answer questions in a real way, to give you their actual feedback, to tell you about what their classmates went through. And I think, from what I've heard from feedback from the admissions process, like students also appreciate having the access to somebody who's been a student rather than somebody who is just kind of interviewing them. And so that's admissions, and in you as an alum is being having a big say in admissions is also, I think it should be important to you, because like you are a student of this fine institution for 4 months, right? But you're going to be an alum for a very long time afterward. And in a sense, this, the name of Full Stack or Grace Hopper will be on your resume for a long time. And so I think we're in this together in that, what happens to that name, how valuable that name is, should be important to you, right? Like whether in 2 years, if you're applying somewhere, if somebody looks at that and says, that was, that is an impressive brand to be associated with, or is it something that has gone downhill and now it's kind of like, I won't name any other names of other schools, but so I think it should be important to you, and I think that's why admissions is very important to me, is because Full Stack, the brand, is like the two things I always remind myself of is that alums are Full Stack to the world, even though to us it's the school, and the school is really what shoots everything off. But the brand of Full Stack is represented by the people who are in the industry, who are doing, who are building things, who are eventually moving up in their careers, maybe hiring out of here or other places, etc. And so I think admissions is important. Then the next thing is development. It's possible, and this is not a guarantee, but it's possible that you may get to spend some time working on full stack development projects. Like for example, things like LearnDot, AssessDot, even our front page, and a lot of other software at full stack had heavy contributions from fellows, of course, right? And so, however, I should say that the primary goal of the fellowship is not to compete with a development job, right? And like, so what does a development job feel like? Well, you kind of walk into work, you go to your desk, and you write code. And that's also a lot of fun. And you'll be doing a lot of that in your life. But the fellowship is all about interacting with people, with students, with other fellows, with instructors, thinking about curriculum, thinking about like how do I reverse engineer this thing that is so easy to me now, but that somebody is struggling with, that I can, how can I explain it to them in a way that makes them not frustrated about it. So like, those are all the things that the fellowship is about. I think development is also something that you will be doing just because you're a developer and you don't need anyone's permission to be a developer. But I should say that it's not like, I don't want anyone to walk into the fellowship thinking that I'm going to be spending all my time coding, right? Because that's not true. But you will get, it's possible that you'll get a chance to work on some full stack software. Otherwise, I've also seen fellows work on their own projects after hours. I've seen fellows themselves do like a second capstone where they come up with another cool idea and have and get to build on it and get some longer time to work on it. I think all those things are great ideas. And then the fourth thing, which is listed fourth here, not because it's fourth in importance, but it's because it's somewhat intangible, but it's that fellows help define the culture of full stack and great software in a very big way. A lot of the really key cultural moments of the experience, like for example, Hot Seat, right? Like Hot Seat was invented by a full stack fellow. And it's something that I think has become so important to how cohorts get to know each other, right? And I think so you have, because you have the closest eye on what the experience is at this moment, having just gone through it, like, we listen to you a lot about how to shape it going forward. So that's kind of the general, so this is the bullet form. And this is sorry, there was like a wrong order of slides, but this is kind of the table form of what you'll be doing. In a sense, the fellowship is also broken up into the junior phase and the senior phase, just like your student experience has been. Both in the junior phase and the senior phase, you'll be working on instruction and admissions, and engineering as much as you can. But in your junior phase, you'll have a learning team that you'll be leading, and then in your senior phase, you'll have a technical project team that you'll be a lead of. But otherwise, you can see that. By the way, this diagram is not like a really hard and fast, and we'll talk about this, about how, in a sense, you can kind of customize your experience about what you want to focus on, what you like doing. So, why you should apply? I think these are kind of some general things. And I think each person will have different reasons that really appeal to you. But I would say that in general, that teaching is a really powerful way to get to know the material specifically, but also to build your leadership skills, to improve your communication. Things that are not things that you already know, but we don't often get a chance to mentor someone, to teach someone. It's a immediate opportunity for putting yourself in a place where you are a leader to some other people. That people look up to you as somebody who they take cues from about how to behave, how to be, what are things that are important. And I think that's important. You'll get to go deeper in your training. So all the things that you've worked on, maybe you haven't had a chance to go as deep as you'd like in a lot of the aspects of the program, and this is, in a sense, another chance to go even deeper. You'll get to meet multiple classes of students in your fellowship, so it'll be another chance to expand your network beyond the cohort, your own cohort, and then finally, again, the intangible is that you get to make a real difference, and yeah. So here are the kind of the program logistics. The total stipend for the program is $10,200. It's considered a internship officially, and the reason it's considered an internship is because it starts and ends at like a specific time. Like it's not an indefinite full-time role like a normal job would be. Also, this is how the paychecks are broken up. Now, you may be wondering why I've put the exact amounts, and I think so. A few cohorts ago of fellows, we learned that for many fellows, this is their like first paycheck ever, and so things like income tax or things that like if you've worked before, you already know about are surprises, and so in the beginning of the fellowship in the orientation, we'll talk a little bit more about this, but we just want to tell you exactly what's going to happen. So like as a junior fellow, you'll be paid $680.23 per week, and as a senior fellow, it's $906.40 per week. This is like normal pay, so it's it's just like a normal paycheck that has income tax and stuff taken out of it as well. And any questions about the stipend portion? Yes.
So are those numbers before or after taxes?
Those are before. So these are broken up and they total this amount. Yeah. For the 13-week portion.
Why is it different amounts in the different accounts?
It's broken up this way in a sense because like you're better as a senior fellow, and so we kind of increase your pay that way. Yeah. Okay, so I'll move on to hiring days. So this is a popular question, but so for hiring day, you will get to do hiring day in its full glory when you graduate your fellowship. In your with your current class, you will get to do demo day in the way that to present and then have a nice recording and stuff like that of the project you've made. When you graduate from the fellowship, you would be doing hiring day. Another question people usually ask is, what will I demo when I'm doing fellow hiring day? And I think right now fellows don't demo anything during that. And while that sounds bad, or it sounds like it's a disadvantage, it's usually not a disadvantage at all. Like fellows tend to be always do well in hiring day, and always be like, it's pretty easy for fellows to stand out in hiring day, and so not participating in the demos doesn't have much impact. And the reason we don't participate in the demos is because oftentimes like the rest of your team may not be a fellow anymore, and so like the way you'll be presenting your project. And also, by the time you're a fellow, you may have other cool things to talk about as well beyond your capstone. So for all those reasons, fellows don't participate in demo day, but they do participate in the hiring day. If you are a remote full stacker, so if you're listening right now and you're a remote full stacker, then you must be willing to move physically to New York or Chicago in order to do the fellowship. And if you want to be a fellow for the remote program, then since that program is run out of New York, you must be willing to move to New York. And so this seems counterintuitive, like why would a remote fellow need to be physical? But the reason is because the whole team is physical, and there is a lot of to run a tight ship, to really keep in touch with everyone. Like the staff needs to be here, and being able to, keep in touch with each other, deal with situations quickly, things like that. And so we want the fellows to be physical. Also, last point that doesn't apply to a lot of people, but if you need to have work authorization in the U.S. to participate in the fellowship. We cannot do any funny business to have you participate in the fellowship if you're not already. So usually somebody always asks me, but I'll just tell you right now, we can't do anything too interesting. All right, so the application process is that, so today, we'll get to talk about it. Hopefully you all will have some good questions that we can talk about. And then we will email you a link to the application, which is due next Monday morning. And the application is important because I think just filling out the application, you will get to know whether you would like doing something like the fellowship. Because it's really for, I think like the kind of person who likes, if you like working with people, you're interested in kind of being a mentor. If all those things kind of sound exciting to you, then you'll enjoy being a fellow. If those things sound stressful and really annoying, then you may be amazing at a development job, but you probably won't be good and be happy as a fellow. So I think if you look at the application, there's a few questions. If you look at the questions, hopefully just the act of filling it out will let you know whether this is something that you'd be interested in. Then next Tuesday and Wednesday, we will have quick interviews for the fellowship. We have two goals for the interviews. One is to really not waste your time, meaning that we don't want you to do any like big prep and stuff like that. So there's really nothing to prep for. There's you can kind of just come right into the interview. And the second thing is that we want to see your teaching and kind of explanation skills more than just your raw development skills. I mean, I think your development skills we already have insight into, but so one of the key things that you'll do in the interview is teach the interviewers a somewhat simple solution. Like, I mean, it shouldn't be like. Let me just say, if you struggle with the actual solution to this, then there's probably other problems that we have to worry about. But like the more is like, how would you explain this to a new student? And that's something that we will, hopefully get to observe. And then we'll talk about some kind of general behavioral questions, and then talk about some of your goals for the fellowship. And so hopefully it should be pretty short. It shouldn't need really all that much, or really any preparation. And then soon after that, we will. Announce to the rest of the class who the fellows are. So, any questions about the interview process? Yes.
This is teacher technical interview question. One that you've never seen before is like, quick, try to teach something you've never seen before, or one you had time to practice with.
I think it'll be something that you've seen before, in the sense that is it still what I think it is? It is, right? Omri hasn't been paying attention, so yes, I think you will have seen it before. I mean, I really don't think the technical problem will be what you're struggling with. It's more like just how do I explain it to somebody who's pretending to be a beginner. Yeah.
And that's the first goal, teach technical.
Yes. Yeah.
Yeah. I'm also pretty sure we should confirm this with Gabby. I'm also pretty sure we send out like here's what to read beforehand of just like these are the problems we're going to go over.
Oh, okay. Okay. Okay, yeah.
Bring it on you. We're just trying to.
Yeah. I think Gabby's about to say something. Yeah. Have they not been able to hear me? Oh, I see. Yeah. So sorry about that. What Gabby said is that we do send the questions that you're gonna have to teach to you beforehand. But they're, like I said, the goal is not for them to be technically complex. It's more to see your teaching skills. Any other questions? I think my next is just questions. Yeah. So, any other questions? Yeah.
So when would we start? What cohort would we start with?
So the question was, when do you start, and how soon will that be? I haven't been repeating the questions, by the way, which is my mistake. I'm really sorry, remote students. So you would be starting in the cohort immediately, the one that starts basically the week after your graduation. So you graduate, then there's a review week, and then whatever cohort starts, that would be when you would start. Yes? That's okay, I'll repeat it, don't worry about it.
What are the traits of a good fellow?
So the question is, what are the traits of a good fellow? I think, I mentioned some of them. Like if the idea of teaching someone, working with a group of students to help, to take them through kind of the things that they're struggling with, to take 3 months to focus on like teaching, kind of in some of the things that happen in a school around, basically like help me participating in kind of what goes on at Full Stack. If that sounds like a lot of fun, then I think you would be a good fellow. Sorry, I feel like I should have a more. If you were interviewing me, I probably wouldn't have gotten the job. But I feel like I feel like maybe Omri, do you have anything to share about qualities of a good fellow?
Yeah. So I think there are probably like a couple things I would highlight. One is if you're oh right, thank you. Yeah, hi remote people. So one is compassion, I think, is pretty important, and I think a ton of you have that. I don't think that's in anything rare amongst you all. Another thing I think is important is like initiative and working independently. I think some of the most successful fellowships I've seen, people have just like had an idea and they've just sort of gone with it and tried it out one day and like asked like, hey, could I just try out this workshop with the juniors? And we were like, sure, why not? So like, I think those have been really, really successful fellowships when people have just managed to take that initiative. So.
That was very good. Are you applying to the fellowship too? Yeah, I think I know someone. I can put in a good word. Yeah, but that was a very good answer. Thank you, Amri. Yes.
I have 2 questions. Who would be interviewing us, and what is the training process like for a fellow?
So interviewers will be Gabby, along with a instructor. And do we already know who's going to do the interviews? Should we be telling everyone who the interviewer is in case they send you bribes or something? Maybe we should keep that under wraps. But yeah, it's cat's out of the bag. It'll be Gabby and Griffin. And then your second question was about training. So in the review week right after your graduation, there are 2 days that we have. Is it 2 days or one day? Because there's a Learn hackathon on one day maybe. Okay, that makes sense. So then you don't have to take off time during the review week. Okay. Yeah, and so there is this kind of light training session which talks about things like how to like tips about how to work with someone who's struggling, like in the being on an instructional team, some of the logistics around being a fellow itself. And then while you are participating in the fellowship during the semester, like you will know when you are on a team and when you need to prepare to make sure that you know what's going on. And like so like in some ways you'll also be training and working on things during your off times as well during the fellowship. But as far as kind of like a official training day, I think it looks like it'll be on the hiring day. Yes.
Do you get to choose if you place in full stack or
You definitely get to express your preference. Yeah. I guess that's not much. That's not saying much. But yes, we will. You get to express your preference, and we will take it seriously. All right. So I'll give you two things. Yeah. But we can't. I mean, we can't be 100% promise. It kind of depends on who applies and where we think people would be a good fit. Any other questions? You know, I would recommend you talk to current fellows. This probably goes without saying, but that's a very good, obviously, a good source of somebody to know, what it'll feel like, whether you should apply. Also, feel free to Slack me, Gabby, Omri. I think Omri probably, he seems to know more about the fellowship than me. But yeah, definitely feel free to get in touch with us, and yeah, and look out for the application. Is that it? Any other questions? Final? I saw a lot of people about to clap, but one more question. Yeah, yeah. Good question. So I don't have a good answer for you. The question was how many fellows would there be? We will look at. So we have to look at what the student numbers are for the upcoming course. Once those are finalized, then we will have a good idea of how many fellows we'll take. It's going to be around 10-ish. Is that fair? Something like that. Yeah. Yes.
What performance data is looked at closest? Maybe checkpoints, or what do teachers say about you?
As far as the actual selection process? So we definitely do take recommendations from your instructors. I think that I think that's definitely there. But also how you do on the interview. I think that is important. We don't get too many instances to see how you will approach teaching something in a very kind of focused way. So I think that is a very important data point. There's also a debugging question on the where you're kind of simulating doing a help, right? Doing a help ticket with a student, and so how you do on that is also an important part of the process. Yeah. Yeah. Also, if you wear a suit to the interview,
it won't have any impact.
Yeah. Yeah, it won't have any impact. I was just hoping I could convince everyone to wear suits to these interviews. Okay, that would be funny, right? That would be funny. Yeah. Okay. All right. Any other questions? Was that a hand raise or a clap coming up? All right. Thank you, guys. That's it. It's over.
Is there a clicker? A clicker, you know, the presentation clicker somewhere? I didn't see it up there. Maybe it's hiding. He's getting it? Okay. Oh, okay. If there's one, that's okay. Yeah, it's okay. I'll just hit spacebar. No worries. All right, everyone. Welcome to the second installment of this CTO talk. I delivered the first one, I guess it must have been about 6 weeks ago now. And so when I agreed to do it, it's like we were sitting in a staff meeting and someone was like, there should be a new architecture talk, or a new talk on architecture. And I was like, oh, I'd love to do that. And then I almost immediately regretted it because I realized I don't know how to talk about computer architecture, which is probably not a very auspicious sign. You might be like, so why are you standing here at 6 p.m.? Because there's just so much, right? There's like all these different design patterns and different ways of approaching problems. It's like I could stand up here and like just talk about Bloom filters for an hour, and I promise you, you don't want that. And as I started to think about it, I realized that more interesting than the finished products of architecture, so we think about this. We think about like impressive blueprints, impressive buildings, but those are all the results of a process. And that process is actually the interesting thing. That is something that you can learn and internalize. And so what I'm going to offer to you in this talk is, first of all, some interesting stories and some ruminations on life. And then also some hopefully useful tools that you can bring to the process of developing really any system, but software in particular. So first, I want to ask you a question. And that question is, how do you learn? And I will try and feel free to yell out or raise your hand answers, and I will try and repeat them. Remember to repeat them for everyone who's remote. Hi, remote people. Teaching, right. So one thing you can do is try and teach the thing you're trying to learn, and you definitely learn it better.
Make connections to previous knowledge.
Yeah, you build up, you start to draw, sorry, I forgot to say this, but the answer was you make connections to previous knowledge. That kind of is what learning is, right? It is the act of doing that. What about physical, simple actions? Yeah, Tina. Repeating, yeah. So recapitulation, saying exactly what the person just said, monkey see, monkey do. Those are things we see in play, right? So a lot of animals learn through play. There's all these play behaviors that we engage in too, where some of it is mimicry. You try and do what someone else is doing. And then you set up a system where you can play off of each other in order to try and collectively hone in on some concept, some experiential concept that is at the heart of play. Yeah, Stephanie.
Gaining an abstract concept that you've extracted from repeating a process over and over again.
So abstraction, sort of?
Learning, like when you're learning math, algebra, you have to be able to overcome a barrier of understanding an abstract concept. And to do that, you repeat lots of little exercises.
Right. So basically, repetition. That's what you said. You do something that is not necessarily that high level a lot, and then over time you learn. You sort of start to see the higher order thing come out of it. So yeah, so there's lots of ways that we learn. There are certain sort of general modes of learning. There's like classical conditioning, which we don't really think of when it's not the first thing that comes to mind when we think of human learning, but it's definitely a form of learning that we all engage in constantly, right? We are constantly being rewarded for doing little things, and we build an association that like, oh, if like I hear this bell, then I know I'm about to get fed, so I should start salivating. And then there are other neurochemical processes. There's like habituation, where if you live in New York City, I went to the country recently, and my friends were like, "Can you hear that?" And I was kind of like, no, not really. And I realized later that I could hear that, but I had learned to ignore it. I had actually just basically learned to ignore almost everything I was hearing, because I live in New York City, and if you actually pay attention to everything you're hearing, you will go completely crazy. You will become overwhelmed with stimulus. And then on the other side of that, there's sensitization, where you actually learn the importance of a stimuli. And all of those are at work when we are learning, when we're learning even to code, right? You become sensitive. I'm very sensitive to indentation, something that most people are not very sensitive to. And it's become that way because of this repeated process of like seeing it in one way, learning that pattern, recapitulating it, and then over time starting to feel like one way is right and another way is wrong. And that is good, but it's also kind of problematic, because as we learn, paradoxically, it becomes harder for us to learn, because we start to become ossified. We start to like believe that we know the things that we know, and we lose the sense of play that makes it so easy for kids to pick up anything. So I'm going to ask another question. Why do we learn? Why are you here? Sarah?
On a very like low level, like to survive, like animals.
Yeah, right? No, the answer was to survive, and that's like totally it, right? Like why are you here learning to code? Well, to get a job is a pretty common answer. And why do you need a job? Well, to eat. It's like, okay, same process, different, or like very much more complicated path to get there. But you're right that the fundamental reason we learn is because we are learning systems. We are brains. Learning is what brains do. And the reason that learning is what brains do is because they have to adapt to being in a complex, ever-changing environment. An environment that is ever-changing, incidentally, because it comprises other brains as well, which are also learning. So there's this very large-scale feedback where if you don't get smarter, you had better be bacteria and not need to get smarter. But if you want to interact with the world in a macro way, then there's a push towards having to deal with ever-increasing amounts of complexity. And you're kind of the result of that process. That doesn't mean that complexity is good necessarily or bad. It's sort of the end result of a game that we're all constantly playing. And the systems we make increasingly, first of all, learn, and are increasingly pervasive. They are more and more, I don't want to say first-class citizens, because robots are not yet citizens, but someday Facebook will be. But they're more and more agents within our world. And that's the ground framework I'd like us to start from, that when we build something, we're not just building that thing for a purpose, although we must do that. We are building tools for a purpose. We're building things that will have life beyond us, things that will become part of this larger system. And it's important to think about those larger systems in our work. Okay. So this is a law or saying or aphorism that David loves, David Yang. And it says that it's Conway's law. Organizations are doomed to produce designs which are copies of their internal communication structures, which means that if you have a front-end team and a back-end team, or if, in a classic example, some engineers were trying to describe all of networking, and so they split off into 7 working groups. and each sort of tackled a slightly different aspect of the problem. And surprisingly, they came up with a model where there are 7 layers of the network stack. Each one corresponds to a working group. And that's why if you read about, I think it's the OSI model of networking, there are 7 layers. It's because they had a number of people in the room that day evenly divisible by 7, most likely. If there were 81 people, we would be reading about the 9 layers. And a corollary of this is that you are yourself doomed to produce designs which are copies of your own internal processes. If we take you to be something like an organism is what I almost said, an organization, which as an organism you are. And so that means that your internal processes are actually extremely relevant to the design of the things you make. And in particular, I want to call out humility, essentially. Or the ability to act without ego that is important to play and important to learning. Because the moment we start to get entangled with oh, this is something that I have made and it is part of me and I am important, so it is important, and I am perfect, so it is perfect. You might not consciously think all those things. You might in fact say steadfastly refute a lot of them. But we all know the feeling of someone critiquing our work and carrying and feeling like that is a jab against us. And that, I think, is ultimately detrimental. That is why we have failing systems that go off and do terrible things or do not exactly the things that we wanted them to do in the first place, is because we don't engage in this continuous process of asking questions. About which, so here's an axiom that I've heard it stated in a few different ways, and I actually can't find a source for it. If one of you has one, I would love to hear it. But it goes like this. Everything we make must either solve problems or create problems. And creating problems is art, and solving problems is engineering. So right now, we're going to focus on engineering. And we're going to talk about some ways that we solve problems. I think that solving problems the process of it is heavily tied up in the questions you ask. You must always be asking some question that helps you reify or refine your design. And here are a few of them. So the first one, the one that I think is most important in an engineering design process, is what problem am I trying to solve? The second one is, why is this text so dim? It's very strange. But this one is much more important. Because it's very easy, and you're all right at the moment of getting into capstones, which is perfect for this. You're all right in this stage of throwing out lots of ideas and trying to figure out what path to pursue, and also trying to figure out how to pursue it. And in some cases, what you're making will actually be art and will better fit under that umbrella. So there might not be a particular problem that you're trying to solve in the overall app. Particularly games, you sort of engineer a problem. But then once you've engineered the problem, now you actually have a bunch of problems that you need to solve. And it's very helpful to have those drive your process, to always have something that you're trying to answer. And just having a problem is nice, but you actually want a way to talk about that problem. You want a way to characterize it. And a way that I find helpful when programming is to ask, what's my input, and what's my output, and then what is my test? So this is particularly applicable in programming, where we can think about functions and be like, okay, they have input, they produce output, and they're tested, or they probably don't work. Those are basically the 3 features of software development. But it works more generally, too. You can think about, first of all, you can think about software objects that are at a higher level than functions. Even whole systems, whole servers can be said to consume something and produce it, and then somehow be testable. And then even the engineering processes, that is the processes of us working together, are processes that consume input of some kind and produce output and then can be testable. And so I want to take us on a little journey through a couple of case studies. or possibly 3 case studies if we have time. And we'll try and apply this, and also just try and apply the general intuitive process of problem solving to a couple of problems. Does that sound good? Everyone happy? And we're going to do this collaboratively, which is why I'm standing at my computer ready to type. Yeah, that's the first one. OK, so the first question is, wow, that's red. Color balance is very different on the projector. So the first case study, first problem I want to pose to you is I want a real-time database. If you're familiar with Firebase, I'm asking you to design something like Firebase, but you don't have to design it in the same way. Just has to kind of solve the problem. And the problem, if I had to state it as a problem, is like, hey, when I update something in my database, not everyone looking at their screen knows that it's changed. So like if I change something in the customers table and someone else is looking at the customers table, they don't see it until they refresh the page. And I don't like that. So how do I fix it? There's always a big long pause when people are like, oh wait, she's expecting us to to say something.
Have everybody look at the same thing?
Yeah, so one answer is like the answer was have everyone look at the same screen. It's like, okay. So now I have a different problem, which is that some people are in New Jersey and some people are in Sydney, and it's hard for them to be looking at the same screen. Yeah, so.
Initial guess, your database sends out a warning when something's changed, and some intermediate determines when to re-render any output.
Right, so we have something, I don't know, call it a notifier. Naming things is the hardest problem in computer science, by the way. So we have a notifier that I guess it like reads from the database somehow. And maybe we don't know this yet, but we do know that it's going to send notifications to clients. How does it know who it should send notifications to and where? No, but this is good, right? We have like one piece of a solution. Yeah.
I'm guessing you would want like some way of subscribing, and you would probably want to ask with the client's permission, like, can I just send you data in the future without you particularly asking for it?
Yeah. So the answer was like we should have some kind of way of subscribing. So maybe we have we'll say that the notifier knows who has been subscribed, and maybe there's some other piece, the receptionist, that takes a client who connects to it somehow and outputs some subscriptions. And so now we have these two pieces, and we've defined how they're going to work together. And we can sort of flesh out the details later. Like probably one of these is, or probably these are both front ends, right, that you will need to connect to. OK. What about, like, is that even sufficient? So does that answer our use case? Make a compelling case for me.
It answers the first part of people will know something has changed. They may not necessarily know what's changed.
Right, people will know something has changed. They don't necessarily know what's changed, but maybe that's OK, right? Because they can just go re-request whatever they were asking for. OK, so let's say we can write this, we can deploy it. It seems we can kind of imagine writing like an Express server that does this. And we do that, we deploy it, and the database starts to burn to the ground. Like particularly, because now all of these clients, which were just like happy to be looking at a fixed screen, now whenever anything changes, everyone reloads the page. And in fact, they basically do it at the same time. So we get these big spikes of activity, which means that the database server falls over. So one answer could be, well, go buy more database servers. And then I'll say that there's another problem, which is that our clients are like, now your product is too expensive because you need like 50 database servers. Yeah. So the question was, does it count as real time if it's not immediately concurrent? This seems good enough, or at least plausibly good enough, because nothing is immediately concurrent, like Einstein told us that.
So, couldn't you just, like, if someone's not looking at that piece of data, then you wouldn't have to tell them kind of
Right, but then we need to know what you're looking at. So now I guess we have to say that a subscription is for some piece of data. And now we kind of have to decide how we architect our data, right? Like, how do you say, oh, I'm interested in this? And so we might say, like, okay, if we already have a relational database, it might be reasonable to say, like, okay, you can watch a query, right? You can, instead of saying select everything from users, you'll say watch everything from users. We'll just update the protocol so that that's something you can do. That's fine, but it is very hard to implement because I might be selecting something and it's not clear all the data that it's going to need, right? Or it's a rather complicated query and I have to keep rerunning it. So one example might be if I have some like big select everything from users group by blah, 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 blah. And then this thing has some aggregation function. And the results of this function determine the groups that I get, which means that I have to rerun that all the time, basically, for any change to the table, which is still, let's say the database server is still falling over, basically. We're not able to determine granularly enough what people want to watch. Yeah?
When you're publishing bonus change, when you're doing publishing of those change, putting the level of bonus change, and you find things that fair enough requests version of it.
So when I make a change, what was the second part?
So when somebody makes a change, it goes to the database, and the database publishes to all the subscribers.
Mm-hmm.
Normally, when they're publishing, when you send out a notification to subscribers, you can let them know what was changed, so that they can decide whether to
Right. So we'll say that that's part of this, right? Like, since subscriptions include this, notifications, yeah, notifications should also have what changed, and maybe even the new value at this point. We know you're about to re-request it anyway, so we're just going to include it for you. But, oh, crap, I keep trying to save. So a fundamental problem here is our data model has kind of become unwieldy. Like, we can't support this data model while being real time. So we might pick a different one. And now the fact that I've picked kind of an abstract use case is hard because it's hard to say like what a good data model would be. But we can think of some in general, right? We could have a much simpler data model than a relational database that's just like a key value store, right? So you store, it's like a giant hash table, and if you change the value at some key, then we'll let you know if that's changed. And if we do that kind of thing, then we'll have Redis. So examples. So if I have a watchable key value store, I get Redis. We might then say, if I want to, we might want more complexity in our data model. We might want to be able to like compose these key value stores and say that, okay, at this path, there's another database where we can read and write things. And if we do that, then we have Firebase, basically, or any kind of real-time file system. So watchable, hierarchical, key value store, Firebase, Spanner, etc. And if we decide on something else, Like we might say that for our use case, a graph is a good strategy. Then like we want to be able to represent a graph of data. Like for example, perhaps we are Facebook and we want to store all of the friendships in the entire world somewhere and have them be real-time accessible, which kind of they are. Then we might end up with something like Facebook uses, which I don't know what it is, or like a graph database like Neo4j. Graph Facebook's craziness. What is it? I don't know. So does this feel like a more tractable problem than it did in the beginning? Great, we're winning. We're totally winning. Like if it seems like you still definitely don't have like all the questions answered. Like if you sat down to write this as just a single Express server, you would immediately be faced with a bunch more problems. But you kind of have a framework to work with them in. And then if that got big and you started to have to think about scaling it horizontally or vertically, then you would be faced with even more problems. And that's fine. The point is that we've made some progress. We've like chipped away a little bit and now have some kind of structure to work in. Problems are not bad. Problems are great. Okay. Questions about this case study? Let's look at another. Okay. My next case study is for a radiation therapy machine. So user lies down on table, machine like positions head, zaps them with an electron beam, and then stops zapping them with an electron beam. Should probably only zap them with the right amount of radiation. Not more radiation, and also not less, if they're supposed to get radiation. So what are our concerns with this? Yeah, Kate.
You want to have like a focal point of where the radiation should be focused? The whole body?
Yeah, so there's got to be a lens of some kind, a lens which is maybe hardware, but probably there's like a targeting system which does something, right? It needs to take like a point somewhere on their body, and then it needs to talk to some hardware to move stuff into position. Hardware, I'll just say hardware commands. Okay, that's important. Yes?
Is there a radiologist example?
God, I hope so.
So it's looking in the user interface, right? For looking at, I guess, our algorithm's recommendations for what his calibration, I guess, level should be, and then also where he should put it.
Yeah, absolutely.
But he should also be able to sort of adjust for, like, if the machine is terribly wrong, he should be able to fix that.
Yeah. So the input of this is like an interface. It's really a radiologist. And the output is a point for the targeting system. What was the other thing you mentioned?
The ability to sort of, I guess, both view recommendations from our machine, but then also alter them in case they're wrong. So,
Yeah. So this may or may not provide like dosage guidelines. Oh. Yes, Steph.
Can we assume the person's immobilized, or would we also have to handle their movement?
I think you can assume that they're either sufficiently immobilized or it doesn't matter. Stay very still. I'm making that assumption because I don't think most of these systems have cameras as is. Like they don't really detect your motion. They just hope that you don't. But that's a good question. Yeah, Sarah.
You would need a timer for like start zapping them now and then like stop zapping them.
Yeah. So this is like a pretty important thing. It's like the what would we call it? Timer seems to somehow understate it, it's like the firing system. There we go, which probably takes a dosage and then outputs hardware commands. So this will go to positioning, and this will go to the beam. Are there any special concerns with the firing system? What are they?
Run away.
Yeah, it's scary.
Well, the system's three-dimensional, so you need to start with an idea of what you want to cover. You need all of that information, and then you need to keep track of where you've been. So.
Right. So that sounds like something in the targeting system, right? It needs to know. So maybe it's not a single point. Maybe it's like a collection of points. But let's keep it simple. It's like if they want to dose another area, they pick a different area and like go through the whole flow again. Sure, it would be nice if it did more, but really, in a radiation machine, I want it to do as little as possible. So this is at least a start, right? This gets us to somewhere, and we can like make something and test it and iterate on it. Okay, the last case study I want us to look at is maybe not software at all, but I want to make decisions. Like I want to probably not have a robot tell me what to do, but rather I have a group of people and we're trying to figure out what to do. You might be familiar with this problem right now. So what are some good ways to make decisions? Yes?
Have a problem?
Yeah, so have a problem. The problem. What is interesting about the problem? What does the problem tell us? You think there's a solution? Like, why? So when I said like you should have a problem, or what was it exactly I said? Like, what is the problem you're solving? Why is that important to keep in mind? What does it give us other than sort of a vague sense of direction? Yeah. Yeah. Ooh, that's very well said. So you said the contour of what needs to change. Can you elaborate on that slightly? Yeah, so what needs to change, what does not, and yeah, and it's kind of the test, right? It's kind of how we know that we've made either the right or wrong decision. Also, it tells us what the parameters of the decision are. So like fast, slow, everyone needs to be on board, or like almost nobody needs to be on board. I don't know if that's really a way that people like to make decisions. I'm trying to make the least popular decision I possibly can. So what if we answer some of these questions? What if I say, I want you to make a decision really fast? Or I want you to design a system that can make decisions really fast?
Do we know that they need to be like good decisions, or can they just be really fast?
That is such a good question.
Right, wrong.
Yeah. They need to be. It's such a good question. They have to be right, but at least some of them are very, very important. Some of them are not very, very important. You don't really know which ones are which. But in all cases, speed is important. It's more important that the process not get blocked than, so like think about medical triage. Let's maybe constrain it to that. Like, sometimes making the wrong decision is really a bad thing. Sometimes it's not really a bad thing, but in any case, sitting around like waiting is definitely probably the wrong path. There was a hand up there, yeah.
Don't we need to know the user, like, what, like the data about the user, what he needs. The user is finding a problem, and then we need the data.
Yeah, so you need to know something about, if you're designing like a software system to do this, then absolutely you need to know a ton of information about like what kinds of responses constitute good decisions. And actually you need to know that for people too, right? So can I sum up what you said as like data on what constitutes a good decision? Yeah, we absolutely need that. Yeah, Steph.
Just say we need goals and desires.
Yeah. This is another way of saying, this is a way of articulating a goal, I think. Let's talk about various strategies we might have to make decisions. Yeah, Sarah.
Do you find like the top 3 solutions? Like, would you be able to just like, as the software, be like, these are the top 3 solutions, and like the probabilities of it being the right one, or is that going to be too slow?
So let's think about human processes for this one and not worry about software. I think we can implement it in software by just training a neural network to do it or something. But yeah, no, you can. So the question then is like, okay, so here's one process. Take the top 3, decide between them. How do we take the top 3? Yeah?
Just start with any random changes and then see if it gets closer to if it passes your test better.
Yeah, you could have, so like randomly, lookup table is, I think, it's basically an incarnation of what is used in triage to some extent, right? When you think about medical training, it's a lookup table. Basically, you're learning, like, if you see this and this, you need to like apply pressure here. Or if you see this and this, here are the 3 things to look out for. Who does the deciding?
Deciding is just whoever has a goal or problem and a way to test it just executes that. There's no computer, right? There's a person.
Well, let's ground this in a concrete example. So let's take triage and say like, this building is on fire and there are wounded people everywhere. And you're outside of the building. That's important because the decisions are really easy if you're inside the building. Don't be in there. What do you do? Like, how do you manage that system? Yeah.
You would sort of like rank the immediate people near you and see who is in the worst shape, and then go to the person that seems to be in like the worst shape, and that's how you decide like who to go to first, I think.
Yeah, so this is, if you are a care provider, you engage in a process of triage. But even before that, there's this question of like, how do you keep utter chaos from happening, basically. Elsa, did you?
I was thinking of like deciding how, having a system for how, you asked like who makes the decision. So like some groups, there's like one leader or a hierarchy, or like do you have to wait till there's full consensus? Or like is there majority vote?
Yeah, so you said like 5 great things. One was like hierarchy is one answer. Where it's basically one person at the top, more under them. Consensus. Voting, I think, is one of them. We could vote. This These are definitely slower than, oh, I guess there's one I missed, which is autocracy, which is one person at the top, nobody else. So this is very, very fast, actually. Or it's assuming everyone makes decisions at about equal speed, that one is going to be the fastest. Which, that seems clear to me. Is that clear to everyone? Yeah, because like you're trying to do a consensus process right now, I assume, and you're realizing that it's not necessarily that fast because everyone has to be on board, and the very process of forming consensus involves making many decisions. With autocracy, it's like just one person, which is great, gets the trains running on time. Not so great if you want buy-in. So a hierarchy can be helpful in that regard because at the very least, it's not one person, it is many. Also, you don't have the same bottlenecks you do with one person, right? The main reason companies aren't just straight up autocracies is that one person quickly runs out of the, what's the term I'm looking for? They run out of like decision-making points. You just don't have bandwidth. That's it, thank you. They run out of bandwidth and the ability to process all the information going through the company. And so you create a hierarchy, which gives you a lot of the speed of autocracy, but without, with more bandwidth, you can always scale it to more layers. The downside being that eventually it becomes so deep that you don't know, the top parts don't know what's going on with the bottom. You basically lose information as it comes up. And then there's obviously a bajillion voting systems, each with their own pros and cons. So I brought this case study up, one, because I want us to think about social systems in addition to engineering systems, and two, because it actually, these are all kind of models that you start to see in distributed processing. And they all have similar benefits and drawbacks. Like if you have like an elected master system where there's one system, there's one machine that is the leader, and all of the others are followers, it responds very quickly because you always know who you should be talking to. But if anything happens to that machine, it's utter chaos. And that machine can quickly get overloaded, again, leading to utter chaos. Hierarchies are a way of solving that, but you still have the problem that if the leader at any point in the hierarchy goes away, chaos again. And consensus and voting systems, you see, here I'll type this out, Paxos. The Paxos distributed computing architecture, I think, is basically based on different ways of forming consensus between a group of machines as to how to move forward. And it would be nice to say, like, oh, isn't it cool that we came up with the same solutions in human systems and computer systems? And it is kind of cool, but also we were people first, and so kind of we went and implemented these systems in computer systems. There might be much better systems for computers that we just haven't come up with because we're so bound by what we're expecting, how we're expecting to organize things. All right. That is it for our case studies. Any questions before we move on? Okay. Yes. Okay, so I have some bad news for you. Your patient has died. So you got a report saying that there was a guy who was being treated by your radiation therapy machine. And during his treatment, he screamed, he asked the radiologist if she had hit the right button, and he ran out of the room. And then 3 or 4 weeks later, he started showing signs of radiation poisoning and died a week later. Oops. So this is, someone probably had this suspicion when I said radiation therapy machine, but there's a very famous case study of a machine called the Therac 25, which injured 6 people and killed 3 of them by delivering them like 100 doses 100 times greater than they were supposed to receive of radiation. In fact, doses that nobody should have been receiving because the machine was not even in the right mode. It had two modes of operation, one in which it delivered electron beam radiation and one in which it delivered X-rays. And due to a concurrent programming error, if the operator hit just the right set of keystrokes at just the right moment in time, the system would switch its beam to the highest power, which is needed for X-ray mode, but not swivel the X-ray bits of hardware. It's like a piece of metal that the electron beam hits that causes it to emit X-rays. Wouldn't swivel that into place, and so it just zapped them. One of the patients who was killed by it joked that Captain Kirk forgot to set phasers to stun, which is dark, but at least he has humor about it. So software engineers love to bring up this case study, both because it is actually like genuinely weighty. It's like, oh yeah, you can build software that kills people. Most of us, and it also makes us feel kind of important because most of us will never write software that could potentially kill people. Thankfully, right? I don't want to be writing the self-driving car software. Interesting side note, I went and looked into their code base when I had access to their code base. All the software at Google is like in one giant repository, so you can just go like poke around. And I was expecting to see like a lot of, I don't know, sort of neural network, like learning stuff and this and that. And there is that at the lower levels where it's like, do you see a person in this scene? A lot of that is trained. But then the code I was looking at was like 500 lines of C++ on how to make a left turn. Like, like literally check to see if there's a pedestrian in the way, check to see if this and that. And I'm sure there's like several layers of interlocks, but oh my God, can you imagine writing that code and having to, every time this machine makes a left turn, you have to sort of hold, like clutch your heart and hope that everything goes right and nothing goes wrong, because something going wrong could mean someone dies. And one of the major contributing factors, so anything like this, there's supposed to be many layers of safety, and so therefore many things have to go wrong. So in some of the cases, the intercom wasn't working between the patient and the radiologist, and so, or the tech, and so they would administer a dose. The patient would scream and be like, that's not okay, and they would administer another because they just can't hear it, which is horrifying. And in the software itself, there were two bugs, actually, one of which was in code that had been in use for years and years and years, and that the bug just hadn't manifested itself, or it had sort of manifested itself, but it had been masked by the fact that previous models of the machine had a hardware interlock, like a physical switch that if the plate was not swiveled into place, it would not go into high power mode. But the hardware interlock didn't have any way of saying, oh, I've been triggered right now, like you tried to do the bad thing. And so people copied the control software from previous versions, thinking it was good. But the control software was constantly failing, and they didn't know it. And then the last, one more thing is that like the machine also flagged an error when this happened, and it was an inscrutable error, malfunction 54, and the technicians quickly learned to just ignore malfunction 54 if it happened, because the machine was fine. And then finally, the engineers at the like Canadian radiation therapy, like medical devices company, said like they received reports of this and then initially did not believe them because it seems very improbable, and they were very attached to their work. Okay, so in the beginning, I brought up this dichotomy. I said that engineering solves problems and art creates them, which sounds like a dig at art a little bit, but it's totally not. Because I think that creating problems is actually one of the most important things we can do. Art seeks to emerge into consciousness elements of our experience that usually lie beneath it. So you might not think much of the color red used extensively in this presentation, but when you're in the same room as a Rauschenberg, it makes you ask those questions. And I think the things that we do, the things that we make, should make us ask questions about our world. Problems give us a set of rules, and they give us a space in which to explore them, and they give us those questions to explore. So they are like a foundational element of inquiry. And this is not anyway a dichotomy, right? Like you might have noticed that the process of engineering creates radically more problems than it solves. Like calculus created an infinite number of problems and has solved only a few. And hopefully the same is true for art. So this was on the title slide. Does anyone know where this is? Yeah, it's La Sagrada Familia, which is a beautiful, beautiful building in Barcelona, Spain. And so this is the inside. It's held up by the roof is held up by these branching geometric pillars. Inside, it kind of looks like you're inside the mind of an angel. And on the outside, which I didn't find a good picture of, it's like this deep brown, colored like the earth, hallucinogenic collection of religious imagery. And it looks like the building is sort of erupting itself out of the ground. And in a sense, it kind of is, because everyone who was ever involved with conceiving or starting this project is long dead. It was designed by Antoni Gaudí, who passed away like very early into its construction. It was taken up briefly by like the King of Spain or something, and then like some general. And anyway, it's not anymore run by the government or anything else. It's in fact run by like a few architects who are now like the second or third generation of people to be attempting this project. And it's completely funded by visitor tickets, which means in this very real sense that this is a building that is building itself. It is like funding its own construction. And it is an idea so very attractive that people who have the skills to make it happen are like flocking to the building, like to the idea to make it happen. And so I thought it was a particularly appropriate thing to put on the title slide, because we should seek to make things like that. We should seek to make things that have lives beyond us. And doing that is also a terrible responsibility, because they will do things that we don't expect. A self-driving car is definitely going to run someone over someday for some stupid reason. And maybe on the whole, things will be better with self-driving cars, but that's still a responsibility that we as engineers have to carry. And one way around it is to be like, I teach web programming and I don't write those things. And another is to carry that responsibility in a very real way, but also lightly, understanding that we are all a part of this world and our creations are going to be a part of this large and ever-growing, ever-changing system. That is all I have for you tonight. Thank you. Thank you. Went better than the first. It's over and it went better than the